we are moving from polarization back to FIES. And I am going to talk about how we can observe the evolution of massive stars in just a human lifetime. So V509 Cassiopeia is a yellow hypergiant star. The name hypergiant doesn't just refer to the high luminosity of the star, but it is also a spectral characteristic of it. The hypergiant stars have large-scale motions in their photospheres, and they also undergo rapid changes in that they lose a lot of mass in a very short amount of time. So these stars are in a very unstable state of evolution, and thus we know about 18 of them in our galaxy. And for all massive stars, their evolutionary stage is quite difficult to determine, and that is also the case for yellow hypergiant stars. So during their events of mass loss, the star's physical parameters change very rapidly. And due to all of these cases, the area on the Hertzsprung-Russell diagram where we find these stars became known as the yellow evolutionary void. Yes, perfect. So here is the Hertzsprung-Russell diagram, and the yellow hypergiants have started their journey as massive stars on the main sequence. And from then on, they evolved to become red supergiant stars. In that stage of evolution, they lost about half or even more of their initial mass. And after that, they started to evolve back towards the bluer region of the diagram. In that area, they encounter the yellow void. So, in the yellow void, the star's outer layers become detached from its gravitational attraction, so that the star's effective gravity values can become 0 or even negative. And if that's the case, a star will undergo an eruptive mass loss event. And during that event, the star's outer layers are ejected, and they form a so-called pseudo-photosphere around the star, which is cooler in temperature. So we see that the star's temperature seems to drop. And as the pseudo-photosphere dissipates away from around the star, and we observe it, then the star's temperature seems to rise again. And in this way, the star can bounce back and forth in this yellow void area multiple times. It's unknown how many times it can lose mass in such a way. And V509 Cassiopeia is located on the lower temperature region of the yellow void, along with many other known yellow hypergiant stars. So V509 Cassiopeia is a very bright star in the Cassiopeia constellation, and it is thought that over the course of its evolution, it has lost about half of its initial mass. And recently, there seems to be a bit of a shift in the variability behavior of this star. Also, another interesting property about V509 Cassiopeia is the existence of forbidden emission lines in its spectrum. So these emission lines are usually found in much hotter stars, namely B-E stars, so B stars with forbidden emission lines. And so it's interesting how these lines can form in a cool star such as V509. One of the cases where these lines are found in cooler stars is if these lines are formed by the influence of a hot nearby companion that excites the surrounding medium. However, the companion of V509 Cassiopeia is quite far away, so it doesn't quite explain the appearance of these lines. So here we can see some temperature data from Tartu Observatory taken with the 1.5-meter telescope. And the temperature was found based on a couple of temperature-sensitive spectral lines, namely neutral calcium and ionized iron line. And we can see that over the last about 7 years, the temperature has remained quite stable, about 7,900 Kelvin. But I think the temperature values are put into better context if we look at the historic data. So here is the star's temperature starting from 1950s. And this star, over this amount of time, has undergone 2 events of mass loss. First of them occurred in 1973. And the second one of them occurred from 1979 to 1982. In both cases, there was a considerable drop in temperature, in addition to many other physical parameters that changed over that time. But after the second mass loss event, the temperature started to rise very rapidly, and it reached about 8,000 Kelvin by the beginning of 2000s. So the 2000s beginning data is also mostly from Tartu Observatory. However, it also includes a couple of data points taken with SOFIN at the Nordic Optical Telescope. And since the beginning of 2000s, the temperature seems to have leveled out, but the difference between those 2 sets of data is perhaps that in recent measurements, the amplitude of short-term fluctuations seems to have decreased. So that could point that the star is maybe reaching a more stable phase of evolution. But the temperature changes could be closely related to the star's pulsational cycle. So let's take a look at some radial velocities. Here is also mostly data from Tartu Observatory. However, we have also included some recent data taken with FIES at the Nordic Optical Telescope. And actually, we use the FIES data to better calibrate the radial velocities found at Tartu Observatory, since the uncertainties of Tartu Observatory data are about in the order of half a kilometer per second. And we determine the radial velocities based on a few very strong lines in the star spectrum. This is an example of a silicon line. And you can see the lines in 2 different epochs, about 6 months apart. But to characterize the star's surroundings better, we need some more interesting lines. For example, the ionized iron line. So this line consists of 2 different components. It has an absorption component and 2 emission components in its beam. The absorption component behaves very similarly to the silicon lines that we found radial velocities from. So the absorption component comes from the star's surface and pulsates and changes according to the pulsations of the star. However, for the emission components, we need some nebulosity around the star. But large-scale nebula, that is, can be found in many other yellow hypergiants. It has not been detected around V509 Cassiopeia. So there has to be some sort of smaller scale structure around the star. For example, if it's a disk-like structure, then the emission components are formed further away from the star. Therefore, their location is not influenced by the pulsations, and their velocity does not change over time. And also, in that case, the intensity of the emission components would depend strongly on the location of the absorption component. So as the absorption is bluer or redder, either one or the other emission component will be stronger. And another interesting line is the forbidden calcium line. So this line also is not changing based on the pulsations. There is a bit of a blend on this side because this is another ionized iron line that is somewhat influencing that one. And these ionized calcium, forbidden calcium lines, are often found in B bracket E stars. And in B bracket E stars, it is thought that they are formed in the disks that surround the star. So that would make an interesting connection between the yellow hypergiants and B bracket E stars. So I hope I have given a nice overview about how V509 Cassiopeia has changed recently. And it seems that the star is showing some signs of reaching a more stable state. And from FIES spectra, we can get a little better overview of the star's surrounding medium. Thank you.